Hey guys, today we're doing Chapter 3, Section 8, which is on inverses of functions. So the first question we have is we want to find the inverse of S if S is the set of points 1, 1, 2, 4, 3, 9, and 4, 16. So basically an inverse is undoing what you've already done. So if I think about the inverse of like y equals 3x, well, in the function y equals 3x, what I'm doing is I'm multiplying x by 3. So the inverse of that would be to undo that multiplication by 3, which of course would be a division by 3. So the inverse of y equals 3x would be y equals x over 3. Okay, so essentially in an inverse, what you're doing is just undoing anything that the original function does. So how does that relate to ordered pairs? Well, in an ordered pair, we have our x value and our y value. So essentially, to find an inverse of an ordered pair, all you do is you swap the x and y value. Okay? So if I want to find the inverse of this, I'm going to swap each of these x and y values, and that's going to give me 1, 1 for my first point, 4, 2 for my second point, 9, 3 for my third point, and 16, 4 for my fourth point. Now I need to figure out, is this a function? So remember that in order to determine whether something's a function, that means that for every input you have exactly one output, and that's it. You can't have more than one, and you can't have less than one. So for each of these inputs, do I only have one output? Well, for 1, I only have one output. For 4, I only have one output. For 9, I only have one output. And for 16, I only have one output. So yes, this is a function. Our inverse function theorem states any two functions f and g are inverses if and only if f of g of x equals x for all x in the domain of g, and g of f of x equals x for all x in the domain of f. So essentially what we want to do is we can say that if f of g of x equals x and g of f of x equals x, we know that those two functions are inverses of each other. F and g are inverses if those two things are true. So let's verify that g of x equals 6x plus 5 and f of x equals 16x minus 5 6 are inverses of each other. Well, in order to verify this, I want to find f of g of x and I want to find g of f of x. So I'm going to start with f of g of x. So finding this, I'm going to start by replacing g of x with my actual function. So I have f of 6x plus 5. Now I can plug 6x plus 5 into my f, so I get 1/6 times 6x plus 5 minus 5/6. Now using order of operations, I'm going to start with my distributive property. So if I distribute that through, this gives me x, and 1/6 times 5 gives me 5/6 minus 5/6. You'll notice that those two cancel out and I'm just left with x. Okay, so now I've shown that f of g of x is equal to x, and now I also need to show that g of f of x equals x before I can actually prove that these two things are true. So I'm going to start by replacing f of x in my function here. So I have g of 1/6x minus 5/6. Now I can plug this into my function g, so I've got 6 times 1/6x minus 5/6 plus 5. Okay, now again I need to simplify using my order of operations, so I'm going to start with my distributive property, and that gives me x minus 5 plus 5. These guys are going to cancel out, and I'm just left with x. So now I've shown f of g of x equals x, g of f of x equals x, therefore I know that these are inverses. Now if you actually want to find an inverse rather than just prove an inverse, okay, so this last part, if I ask you to prove that two functions are inverses of each other, this is what I expect you to do. But if I want you to just find the inverse, then it's a lot easier than that. Okay, all you have to do is flip the independent and dependent variables, aka x and y values, and then solve your equation for the new dependent variable, aka y. So if I want to find the inverse of y equals 4 over 3x minus 1, the first thing I'm going to do is swap my x and y values. So I get x equals 4 over 3y minus 1. Now what I want to do is I want to solve for y. So to solve for y, I don't like that y is in my denominator, so in order to get y out of my denominator, I'm just going to multiply both sides by my denominator, which is 3y minus 1. Okay, so when I do that, those cancel out, and I get 3y minus 1 times x equals 4. Now I can divide by x, and that gives me 3y minus 1 equals 4 over x. Now I can add 1, and that gives me 3y equals 4 over x plus 1. And then I can divide by 3. Okay, if I do 4 over x divided by 3, that's just 4 over 3x. And then if I do 1 divided by 3, that's just 1/3. So this is my inverse of my original function 4 over 3x minus 1. We also have the horizontal line test for inverses. Remember the vertical line test. The vertical line test determines whether the function right in front of us is a function or not. So if something passes the vertical line test, that means that it itself is a function. The horizontal line test is reserved for inverses. Essentially, when you have an inverse, what's happening to your actual function and inverse is that they are reflections of each other over the line y equals x. What that means graphically is that it's like a rotation of 180 degrees. So you're swapping your x and y values, which is what we were doing up here at the very top. We swapped the x and y values, or the x and y coordinates, to get our inverse function. So because I'm swapping the x and y values, or I'm reflecting over the line y equals x, what that means is if I were to rotate that vertical line for the vertical line test, basically, if I've got my vertical line here, okay, and I'm rotating it by swapping each of my x and y values, so let's say this is 1, 1, this is 1, 2, this is 1, 3. Okay, if I'm rotating each of those by swapping the x and y values, now the points that I have are 1, 1, 2, 1, 3, 1. Okay, and what that's giving me is it's giving me a horizontal line instead of a vertical line. So basically the inverse of the vertical line test is the horizontal line test. So what we can do is we can use the horizontal line test to determine whether something or not will have an inverse that's a function, or if the inverse won't be a function, before we even have to graph the inverse. So looking at each of these graphs, I want to figure out, is the inverse going to be a function or not? Alright, looking at this first graph here, first of all, the graph itself is a function because it passes the vertical line test. If I want to think about the inverse, I need to think about the horizontal line test. So the horizontal line test, it also passes, therefore the inverse is a function. Okay, this next graph here, looking at it, it passes the vertical line test. That means that this graph is a function. Now, if I want to talk about the inverse, I need to look at the horizontal line test. So, looking at the horizontal line test, right here, it's going to fail the horizontal line test. Therefore, the inverse is not a function. This last graph over here passes the vertical line test. That means that this graph itself is a function. It also passes the horizontal line test. Therefore, the inverse is a function. And that's everything for section 8.